recording. Okay. Chapter 1. Chapter 1 makes a big distinction between two words: microprocessors and microcontrollers. We will not be using these. We will be using those. So I guess it's worth it to think about what the difference between a microprocessor and a microcontroller is. And here's the big difference, all right? A microprocessor, which I abbreviate MU-P, microprocessor, typically will expose its data, its address, and its control bus. Data, address, control. And you have to provide RAM, ROM, I/O, blah, however many I/O devices. You have to provide all of those and then hook them up appropriately. You have to build these things. Okay, a microprocessor is just a CPU. That's it. That's all it's got. It turns on and it starts trying to find whatever's at address 0. So you've got to put in logic here to deal with that. A microcontroller, MU-C, microcontroller, is a monolithic device. It's bigger. And inside of it, inside of a microcontroller, you have a microprocessor. Okay, but inside the microcontroller, you already have some amount of RAM, some amount of ROM, a bunch of I/O things. You could have timers. You could, what else do we have? Serial controllers, an analog to digital converter. What else? Yeah, that's enough. So each of these things already exists inside of a microcontroller, and it's got the interconnections already. Whether it's a parallel bus, multiple buses, you don't know. Probably you don't care. You're just going to use this. Okay, so that's a microcontroller. Everything's already in here, and that's what this is. By the way, later on, I don't know if you can see that. Let's hold on. I can make this better. So this right here is the microcontroller we're going to be using. It's actually, where are we? That little guy right there. Okay, that small chip is a microcontroller that has all of the things I mentioned. Serial ports, timers, I/O controllers. Go back to here and transition. Good. So that's the difference between a microprocessor and a microcontroller. Now, eventually, we will talk about this stuff, okay? But that's peripherals that we'll deal with later on down the line, okay? So a little bit of background about microcontrollers. First off, who makes microcontrollers? Well, most people make microcontrollers. Atmel microcontrollers, and that's what we're using, by the way. We're using an Atmel microcontroller. Microchip makes a series of chips called the PIC. And actually, these are now one company. Microchip bought Atmel. Motorola makes microcontrollers. Intel makes microcontrollers. Oops, Intel Micro. Those are the ones I can come up with off the top of my head. I'm sure that there are some others out there. Usually you'll see them come in 8 or 32-bit variants. There are a few 16-bit variants out there. The 8 and the 32 tell you how big the data bus is. How many bits you can work. Excuse excuse me, how many bits you can work with. So that's the who. Let's look at the internal structure of this. We start with a CPU, the microprocessor inside of the microcontroller. And it is a Harvard architecture. So we're going to have program ROM. And then we're going to have a separate bus that talks to everything else. And it can be any number of devices. And these are bidirectional. So when we have RAM, we have a timer peripheral. Things like interrupt peripherals, interrupts. Most importantly, ports. We're going to be getting to ports sooner rather than later. Okay. Each one of these is what we call a peripheral. RAM is a peripheral. Interrupts are a peripheral. Ports are a peripheral. It's a doodad that we can use. Okay. Now, to do this next thing, I'm going to need to steal some graphics. So let me steal some graphics here so that I can paste them in. That's the graphic I need. You don't have to write this down, but I want you to know that this is the AVR controller that we're going to be using. And there's a lot going on here. We're gonna narrow it down to just a couple of things. First off, there are 3 ports for I/O. Okay, and here they are. Let's go marker red. 3 ports. First is port B. So port B kind of goes along in a backwards C shape. Each pin has a number associated with it, 0 through 7. That's port B. Next is port C, and here's port C. PC0 through PC6. There's only 7 of them, not 8 of them. Last is port D. And there are 8 pins on port D. And they sort of, loop around like that. Green loops around like that. So they're almost contiguous, but not quite. Those are the ports. Now, what the heck else is the rest of this stuff? All of this other stuff is secondary functions. Okay, we're not going to get there yet. We will eventually hit on most of these things. Okay, the only other pins I haven't talked about are these pins here. And those are just your power pins. VCC stands for your positive voltage. Ground is your negative voltage. AVCC is a low noise analog, positive voltage, and so forth. So we've got 3 ports. They can do other things, but at the most basic, they can be high or low. That's it. That's all a port does. It's just pins that go high or low. The name of this chip is called the ATmega 328P. The P stands for pico power. It's a low power variant. All right. Here's next checkpoint. What is the main difference between a microcontroller, UC, and a microprocessor, What is the main difference?
Microcontrollers like all in one, and microprocessor you're providing all the.
Yeah. A microcontroller is a chip that has a microprocessor plus stuff. A microprocessor does nothing unless stuff is hooked up to it. Okay? Describe the port setup of the ATmega 328P. So what can you tell me about the port setup of the 328P? Any facts? No matter how small.
The ports are ATG and they're power pins.
Yeah, so there are power pins, and then you may want to adjust your notes because there is no port A. There's only B, C, and D. Yeah, there are B, C, and D. Some things that might pop out eventually is D has 8 pins. C only has 7 pins. B has 8 pins. Something to be aware of. You'll actually find in practice you have even less pins on port B than you think you do, and less on port C than you think you might. Okay, what other things? Oh, a sort of straightforward question. Is the ATmega 328P Harvard or von Neumann? I think that's an EU. Yes. Is it Harvard or von Neumann? Yeah.
Harvard.
It's Harvard, yes. All right. I think we're going to keep going right ahead. I think we had a little break. Oh, no, hang on a moment. Let's take a moment now to go over here. Nope, not yet. Not yet. We're going to keep going full steam ahead. Full steam ahead. I think we're actually kind of done with chapter 1. Very basics of what's going on. All right. I got to do a little bit of drawing here, so stick with me as I do this, all right? Big box. We're going to graduate now in chapter 2 from our toy CPU to a real CPU. I'm going to start with some boxes here. It's going to be a similar setup. Okay. With a few more bells and whistles, but not too many. And it'll all be things you have seen before, just more of them. And just one more box over here. All right, I'm drawing the straight lines first because I'm terrible at drawing straight lines, but then we can go back to our pen here. All right, so inside of the AVR microprocessor, we still have an ALU, we still have a program counter, we still have an instruction decoder. Over here, I've thrown out my ROM on a separate bus. Right? And the goal is we go ask the ROM for something, and it sends data to the instruction decoder. I've got a new little box here called the status register. Stat register, sreg. It has a bunch of bits in it that are called flags. The flags in question are I, T, H, S, V, N, Z, C. 1, 2, 3, 4, 5, 6, 7, 8 of them. Okay, we're going to get into what those are eventually, but for now, just know that every time the ALU performs an operation, it's going to record the results of the status in this register. The rest of what's going on here is the ALU gets information from the registers. It can both read from the registers and write to the registers. Now, here's our big departure from our toy CPU. Our toy CPU had how many registers? Yeah, 4 of them. Well, we've got so many now, we don't even use letters. We just say that we have R0, R1, R2, R15, R16, R31. We've got 32 registers. Okay. And I will say that we do have over here RAM, and that RAM can receive information from the registers, and the RAM can get information from the registers, and the registers can get information from the RAM. So there's our 2 separate buses, our Harvard architecture, RAM, ROM. Okay, this is what's called the programmer's model. Programmer's model. Tells us everything we need to know to start programming this, except for the assembly language itself. We refer to these guys as general purpose registers, GPRs. That's we're going to talk about other registers later that are called special function registers. These are general purpose. They're used for whatever the heck we feel like. Special function registers or special purpose registers, they have a specific thing that they do, and that's all that they do. Okay. That's exactly the same sheet. We're going to jump right into assembly language. All right, we're going to learn our first assembly language instruction. It's going to be helpful to have this sheet nearby available for you. You don't have to go crazy with it right now. I will tell you that the first instruction we're going to learn is at the top of the 3rd page, so right below the fold. First instruction. You need one? Yeah, come right here. 2? I'll have 2. Instruction. And it is called, you need one as well? Go ahead. LDI. LDI stands for load immediate. And specifically, it's a mnemonic. LDI, load immediate. So this is the opcode, LDI. And we have a format. Any assembly instruction we write is going to follow a particular format. The format for this particular instruction is the mnemonic, LDI. RD, which stands for the destination register. Could be anything from R0 to, well, not actually R0. Any register we can choose, any valid register. And then K8. K8 just means 8 bits of immediate number. So we could say that we wanted to load an immediate value into R16, 127. What that's going to do, it's going to take 127. It's going to shove it in register 16. Okay. Now there are some limitations on this instruction. Some little caveats, little addendums here. And RD must be greater than R16. It has to be R16 or greater. We'll get into this a little bit more, okay? But for now, just know that if you're going to use LDI, it has to reference a register that is greater than or equal to 16. Furthermore, Because this is a K8, K is going to be between 0 and 255. That's a thing that has to be true. With one exception. And here's a short exception. We can express K as decimal, hex, binary, okay? We can use any of these formats. So valid things for K, 10, $1F, OX1F. That's two different ways of doing the same thing. That's hexadecimal notation. We can also put it in binary if you want. 0B, 1, 1, 0, 0, 0, 1, 0, 1. This, by the way, would be equivalent to C5.
Why are you putting in subscript 8?
K8 because it's 8 bits. That's it. There's 8 bits in the immediate value. So it's a hint that you can only go to 255. Now I've clearly stated the bounds of K, right? What are the bounds of K? 0 to 255. Well, I might have lied a little bit because it's perfectly reasonable to say -1. That bother anybody? I've very clearly given you bounds, and now I'm just throwing them out the window. Well, I haven't really thrown them out the window because this instruction is actually going to assemble to be equivalent to that instruction. Those are exactly the same. Does anybody remember why these two things might be considered equal? I'm going to throw out one word, or maybe a couple of words. That's a big crane. We might have to pause class and just look at it. What's 2's complement? Yeah, representing positive and negative numbers. How? How do we represent it? Well, yeah, we use binary. Let's just go over that real quick because it seems like we may have an issue with that. We've got 1's complement. And 1's complement, if we want to take -1, we start with 1. And we flip all the bits. Anything that's a 0 becomes a 1. And anything that's a 1 becomes a 0. To get to 2's complement, we add 1. So what is this plus 1? Well, it's 1, 1, 1, 1. 1, 1, 1, 1. Now, translate this back into hex. FF. So, the assembler is smart enough to know that if you provide a signed number, it'll convert that into 2's complement. So, valid things that you can throw into this are -128 to +127 for signed numbers, or 0 to 255 for unsigned numbers. That's about all the time I can spend on that today, but if you want a more rigorous thing about this, I can either do it during office hours or we can maybe do an extra video or something. But let me know either via email or after class. All right, so that's one instruction. tell you what we'll do. We'll do one more instruction, our second instruction, and then I will do an in-class assignment so that people get credit. Okay, second instruction. This has the mnemonic ADD. Anybody want to guess what ADD stands for? It's the add instruction. And it adds two numbers. So here we specify two registers, RD and RR. Cool your jets. Yeah, it is add without carry, but I won't get to that for like 2 days. All right. There is an add with carry instruction. This is adding two numbers. And there are no limitations. RD can be any register between 31 and 0. So can RR. 31 to 0. Choose anything. Now, the operation that it performs is a little bit interesting. It says that RD is going to take on the value of RD plus RR. So there's no option here for a third operand. Whatever you give as an operand is going to get overwritten. RD will be overwritten for sure. It's just the way that this works. And now that we've started doing this, I want to go back to LDI. I just want to point out that from now until the end of time, data in these instructions is going to flow from right to left. Whatever is here is going to move to the right. Okay, right to left, always. So if I go to this instruction, it's the same thing. Data is going to end up in the leftmost instruction. So let's give a couple of valid examples here. Add R25, comma, R9. Add R17, R30. It can be anything. An invalid add instruction. Invalid. It has to be registers. You cannot do it any other way than to have two registers. Okay? I really like that diagram, but I don't think it's relevant right now. All right. Grab a separate sheet of paper. If you don't have any, grab some from the printer in the back. We're going to do a couple of problems. Okay, you're going to put your name at the top. If you have a spiral-bound notebook, do not give me that piece of paper. Go get a piece of paper from the printer. Unless it's a flush edge, I don't want it. This is not really to, well, yeah, I guess it is to judge you a little bit. It's here to judge if you are present and if you are keeping up with the material. So it's incentivizing you to follow along and not to sleep, okay, during the class. I know it's tempting. Once we do this in-class assignment, we'll take another break, and then we'll come back, hopefully, for the rest of Chapter 2 and Chapter 3. Okay. Yeah. All right. Everybody got a piece of paper? I've only taught you two instructions. You're only going to use these two instructions to do this problem, or the first problem. Problem 1. Write a program that I will stretch this out in a second. Calculates 19 plus 95. Okay. Second problem, write a program that obviously I spelled it wrong incorrectly the first time, calculates 19 plus 95 plus, oh goodness, plus 5. 2 separate problems. Okay. We're going to do 5 minutes. No talking. Try to do these on your own. And we'll stop recording again.